The racing shell is a high-tech rowboat that's built for speed. Long and exceptionally narrow, it's designed to cut through wave drag and leave the competition in its wake. Racing shells are made for single rowers called scullers, for pairs or entire crews. They're custom-made to precise specifications. Racers need to travel light to maintain speed, so these boats are made from reinforced carbon fiber, which weighs a lot less than wood. First, several of these carbon fiber sheets are layered in a mold and trimmed along the edge. Textured thermoplastic, called honeycomb, gets a spray of glue and is then pressed onto the carbon fiber plies. Sandwiched between layers of carbon fiber, the honeycomb will serve as the shell's core, lending some lightweight reinforcement to the delicate hull. Next, the entire boat is wrapped in breather cloth and a plastic bag so that the air can be vacuumed from between the layers. The breather cloth is a permeable layer that prevents the plastic from sticking to the mold and creating air pockets. Next, the shell goes into a long oven, which melts the glue that's been impregnated in the carbon material, fusing the layers together. The shell bakes at 210 degrees for 8 hours. Then, the plastic and breather cloth are pulled away. And the boat is pried out of the mold using plastic wedges. The hull comes out in one solid piece, and a primer paint sprayed into the mold earlier has adhered to the shell surface. Workers check the weight, which has to be exactly what the customer ordered. Next, they reinforce the boat's cockpit with several carbon fiber bulkheads. Foam is glued on the inside rim of the racing shell using a piece of wood as a guide. Glue is applied around the bulkheads. Then the cockpit panel is lowered so that it adheres to the glued areas and rests on top of the foam that's been installed along the edges. Next, a computerized tool drills holes for the hardware and riggers, and workers trim the rim from stern to bow. They smooth the hull's finish with a grinding tool. And now, it's over to the paint station for some sanding and priming. Any flaws are marked for repair, because the slightest imperfection could affect the boat's ability to speed through the water. Once the boat is perfectly smooth, it gets a high-gloss urethane coating. Next, a fin is installed for a little stability. A laser guide helps align it into perfect position. A rudder goes into the bottom of the boat. The system of ropes that's attached next will allow the rowers to steer. This boat comes with special shoes and sliding seats that allow rowers to put a lot of leg power into their strokes. Finally, the rigging equipment for the oars goes in. Now this sleek racing shell is ready to hit the water.
American Newman Darby built the first sailboards during the 1960s. He rigged his sail to a mast on a board with a tail fin and rode the wind and waves. Today's windsurfers can pay several $1,000s for their high-tech gear. This includes a sail, a mast, and a sailboard. To make a sailboard, workers start with a long block of styrofoam. They attach a wood template, pushing nails through holes in the wood and into the block. Using an electrically heated tool called a hot wire, they slice the block along the curved line of the template. The result is what's known as the core. They use styrofoam because it's lightweight and buoyant. Next, a worker guides what's known as a shaper machine. It outlines a template called a master board on the left, while a spindle cuts grooves into the core on the right. The grooves are guidelines to carve the core into the shape of the master board later on. The shaper's 40-pound counterweight lets the spindle gently hover above the core as it cuts. Styrofoam dust flies everywhere, so the worker wears a protective mask to avoid inhaling it. A worker then saws along the grooves to reveal the initial shape of the sailboard. Another worker then sands down the core. Next, he applies almost 1.5 pounds of epoxy resin onto carbon fabric to reinforce the material and make it sticky. Another worker applies resin on fiberglass fabric. These strong, lightweight materials are part of the board's fabric and foam sandwich construction. They'll harden inside molds of the board's top and bottom sections during the curing later on. The workers carefully scrape away about 20% of the resin. Too much and the board could crack during use. Here, the worker spreads thicker resin onto a piece of rigid foam that's 1/8 of an inch thick. He places it into the bottom mold and attaches a hand-sized plastic component called a fin box. It'll hold the sailboard's fin, which helps the user steer. They add Kevlar, an ultra-lightweight synthetic fabric, as the final outer layer on the core's bottom side. After applying resin to another piece of rigid foam, a worker cuts openings through which other components will later fit. This layer is placed into the top mold and covered with more carbon fabric. Next, a worker places the core into the bottom mold. He fits 2 plastic components called foot strap inserts into openings lined with fiberglass fabric to secure them. Another plastic component called a mast track fits through an opening lined with a stronger carbon fabric. The track will later anchor a mast measuring up to 20 feet high. Strips of carbon fabric also reinforce the areas where the windsurfer will stand. Workers join the mold sections and insert the whole thing into a plastic sack called a vacuum bag. They tape the ends shut but leave 2 smaller holes open. They attach 2 hoses to collars in these holes. An electric pump then takes about 3 minutes to suck all the air out of the bag. As the air is removed, pressure forces the mold sections even closer together. After curing in an oven at 100 degrees Fahrenheit for 5 hours, workers separate the mold sections. Using a rotary grinder, a worker trims away excess hardened fabric and foam along the edge. The whole board got a coat of primer earlier, but now a worker sands the paint off along the edge. They place a strip of carbon fabric all the way around the edge and secure it with thin plastic wrap. After more curing, the wrapping is removed and the board is sealed for good. Next, the sailboard gets another skin, 2 coats of urethane paint. A worker locates the foot strap insert holes and cleans them out with a router bit. He uses a router to clean the inside of the mast track opening. An enormous vinyl sticker gives the board its personality. A worker smooths away any air bubbles. Then, after inscribing the sailboard's dimensions and serial number, he signs the board. Finally, workers glue on 2 rubber cushions called deck pads. For $1,900, you've got the foundation of a very cool gliding machine.
Early in the 20th century, an American biscuit company introduced a cookie sandwich. It was 2 chocolate cookies with rich vanilla icing at the center. This sandwich cookie created an instant sensation, and almost a century later, it hasn't lost its appeal. People still crave this sugary fusion of crunch and cream. Dipping the sandwich cookie in milk is a tasty tradition, and whoever started it must have been one smart cookie. Sandwich cookies start with pure granulated sugar. This worker heaps bags of it into a mixer as he prepares to whip up the batter for the wafers. He adds 2 kinds of cocoa. The combination will give the wafers the desired taste and color. A premix of salt and other ingredients follows. A specially formulated canola oil mixture will transform these dry ingredients into a batter as huge beaters blend everything together. They add water, and the batter starts to look like a bubbling chocolate soup. They add dry ice, which chills the batter as it evaporates. The lower temperature is key, as they add flour to thicken the batter into a dough. The dough will turn out less crumbly than it would have been if it had been kept at room temperature. A premix of leavening ingredients goes in next. One final mix, and this chocolate dough is ready to go. The worker shovels it onto a grate, which protects his fingers as he presses the dough down into a molding machine. This machine shapes the dough into cookie wafers while pressing intricate designs and the brand name onto them. It churns out an impressive 5,000 chocolate wafers an hour. The freshly molded cookie wafers now move from the silicon conveyor to a steel one. It takes the wafers into a gas oven, where they travel in a continuous loop for several minutes to receive an even baking. After that, fans cool the wafers to the desired crispiness. The chocolate wafers then move to another conveyor, which feeds into a series of chutes. Then the wafers travel over ramps designed to make them fall into a certain position. One row lands plain side up, and the next lands with the embossed side up. This correctly orients them to be sandwiched around a cream filling. It's a high-speed operation, as a cylindrical pump deposits the vanilla cream on the plain side of the wafers. The cream-coated wafers head over to the next station. Here, machinery moves the top wafers onto the cream-coated ones. The cookies move up for the count. Mechanical fingers separate them into bunches of 11. Then, grippers swing into action to move each little bunch forward. They release the cookies neatly into plastic trays. The trays, full of sandwich cookies, move on to the wrapping station. Here, metallic film unwinds and wraps around the trays. Hot jaws move in to seal the package at both ends. Finally, they're shipped to retailers. But once these sandwich cookies are in the pantry, it might be tough to keep them under wraps.
A scissor lift is a mobile work platform that rises. The elevating mechanism consists of arms that connect in the middle like scissors, hence the name. Scissor lifts are a common sight on construction sites, in big warehouses, and at buildings where workers need a safe way to reach heights to carry out repairs or maintenance. The number of arms in the scissor mechanism varies according to the height of each particular model. The factory constructs the scissor arms from steel tubes. The first step is to cut them to the right length for the model in production. A worker uses an air gun to blow off tiny shards of metal the cutting leaves behind. The arms go into a press that punches a hole for a hollow steel cylinder called a boss. The boss is the housing for a pin that will connect one arm to the other, yet still allow them to pivot like a pair of scissors. Workers now use a magnetic crane to move the arm to the welding area. They insert the boss into the hole, then tack it in place. This piece will go on the end of each scissor arm, but first they weld on another boss. Now fully assembled, this piece is called the male scissor end. They tack it to one end of the scissor arm and tack a female scissor end to the arm's other end. Robots now weld the two end pieces simultaneously. Then the boss in the middle. Now, workers stack the scissor arms, putting a pin in each middle boss. They also install the hydraulic lift cylinder that will raise and lower the scissor stack. This manifold activates the lift cylinder by increasing and decreasing hydraulic pressure. Workers fasten the connected scissor ends to each other by driving a pin through the boss. They secure it with a locking mechanism called a cotter pin. Meanwhile, other workers assemble the base of the scissor lift. At this stage, it's upside down. At the rear, workers bolt in a hydraulic wheel motor. Hydraulic pressure turns the motor, enabling the operator to move the scissor lift forward or backward. They slide a wheel onto the hub and bolt it securely. This is the wheel hub onto which the front wheel bolts. It attaches with a pin locked by a cotter pin. They install the hydraulic steering cylinder. This steel tie rod links the front wheels to each other so that they turn together. Now, workers hook up the hydraulic hoses. They pump a bit of grease in to lubricate the cylinder. Next, they assemble and install the hydraulic tray. It contains the electrical panel that controls all machine functions, as well as the hydraulic tank and pump. The pump forces hydraulic fluid to the wheel motor, steering cylinder, and lift cylinder. The hydraulic tray swings closed under the base for protection. On the other side, they install the battery tray. It houses the 4 6-volt batteries that power the scissor lift along with a battery charger. The scissor stack, meanwhile, is in the paint booth getting a coat of primer, then a coat of urethane paint. This finish prevents the steel from rusting. After curing the paint in an oven, they install the scissor stack onto the base. Now they connect the two hoses that run between the lift cylinder and the hydraulic pump. Through one hose, fluid goes to the cylinder to raise the scissor. Through the other, fluid withdraws to lower the scissor. They run cables from the electrical panel up through the scissor stack. After installing a platform made of painted steel, they connect the cables to a control box on the platform rail. These controls enable a worker to operate the scissor lift from the platform. After a test drive, it's time to apply the decals, up to 75 of them depending on the model. Some are decorative, but most specify safety information such as the scissor lift's load capacity.
Shock absorbers do more than just smooth your ride. They counteract the bounce when you hit a bump, holding your tires to the road. Without that traction, you could lose control. So by affecting steering, stopping, and stability, shocks are actually a vital safety component. Wheel vibrations cause a piston inside the shock absorber to force oil through a valve. This absorbs energy, reducing the vehicle's bounce. All this happens within the shock's two tubes, the reserve tube, and inside it, the pressure tube housing the piston rod and compression valve. Both of these tubes are made from a steel sheet sliced into strips. Inside this tube mill, coolant prevents the passing strip from overheating as one forming roller after another gradually rounds it into a tube. Then, a copper welding wheel fuses the tube closed. As the 6-yard-long tube comes off the mill, a cutting tool chops it into shock absorber lengths. The tube-making process is the same for the reserve and pressure tubes, except that the reserve tubes undergo one extra step, compressing the ends. This enables the shock to house a larger reserve tube that can hold more oil. The reserve tube's final stop is a press. A die inside stamps the part number, the manufacturing date, and the brand name. Many components are made of powdered metal, mostly iron powder mixed with some graphite and copper. After a press compacts the powder in a die, a furnace fuses the particles. This powdered metal part is the valve through which the piston forces the oil. Steel discs and a spring help control the speed with which the valve operates for varying driving conditions. A stamping tool crimps the end of the tube holding the spring in position. The valve, now fully assembled, seals the bottom of the pressure tube. Meanwhile, a press punches round steel discs into other components. These loops mount the shock absorber to the vehicle. A worker positions a cup on each one, then a robot welds them together. They insert a cup and mount unit on one end of the reserve tube, then weld it on. This unit is called the base assembly. The base assemblies now go on a conveyor, open end up so that workers can drop a pressure tube inside each one. Automated injectors now fill the tubes with oil that's specially designed to maintain its consistency despite changes in temperature. Next comes the head assembly, which includes the steel piston rod and the mount on the other end of the shock absorber. Two copper welding wheels fuse the head assembly to the base assembly with a cap. This closes the unit, sealing the oil inside. Next, workers weld on a dirt shield, a steel casing that prevents dirt from hindering the movement of the piston rod. A piece called a bushing is pressed into each mount. This helps tone down the vibrations coming from the vehicle. Now it's on to an automated carousel. Robots pierce a hole in each shock and inject nitrogen gas to prevent the oil inside from foaming. After injection, the robot seals the hole by welding on a tiny steel ball. And now for the finishing touch, an electrostatic paint job. A machine runs a positive electrical current through the shocks and a negative one through the paint particles. Like a magnet, the static electricity draws the paint onto the shocks in a flawless coat. In the factory's quality control lab, technicians use sophisticated equipment to evaluate how well a shock dampens movement at different speeds. The tube and valve configuration inside varies by vehicle, so the shocks on a ground-hugging sports car are quite different from those on a luxury sedan or on a light truck.